I'm going to talk about an example application for bundle adjustment um, where a vehicle needs to map its environment that it's moving through and also estimate its own self-motion. And this is done using cameras mounted on the vehicle. So here's an example of a autonomous convoy application where the vehicles need to follow a certain path along the road. So one possibility is to put cameras on the vehicle like this. In this case, I put 4 cameras on looking in the various diagonal directions. So bundle adjustment is one way to do structure from motion. It's considered the most accurate way to do this, and it's also very flexible. So it minimizes the squared reprojection errors for the 2D points. So it basically computes the 3D positions of the points and the poses. We can do this for more than 2 poses though. And the unknowns then, of course, are the 3D positions of the points and the relative poses of the cameras. So with 6 degrees of freedom for the poses, we have n minus 1 times 6. And if we have k 3D points, that's 3 times k points or values that we all need to estimate. So we'll use nonlinear least squares. This, of course, is slow. Probably not suitable for real time, although you can do it as a sort of a background process, or you could do it as an offline batch type process. So with this many variables, we'll also need a good starting guess for the unknowns. So here's a diagram of the situation. Here's a camera moving in various poses, unknown, and observing a set of points like this. So the measurements are the image projections of these points at each camera pose. And of course, not every point is observed in every image, so we also need a way to keep track of that. So just like we did with nonlinear least squares estimation of pose, we need a function that predicts the image locations of the 3D points in each of the n camera images or n poses. So the inputs to the function are the current guesses for the 3D points and the guesses for the n-1 poses. So as we did before, we can take the Jacobian of this function and calculate a correction that we will add to our guess and do this until the guesses converge. And just as a side note, there are more efficient algorithms than the Newton's method that we use, such as the Levenberg-Marquardt, which adaptively switches between Newton's method and a steepest descent methods. And this is implemented in MATLAB's LSQ non-lin, which is part of the optimization toolbox. And as before, we have an unknown scale factor in the results. All points and all translations are scaled by the same unknown amount. Possible ways to determine the scale factor: one is to take a picture of a known object in one of the images where we know the coordinates of the 3D coordinates of the points. This constrains the scale in all the subsequent images. We could use stereo cameras with a known baseline that would triangulate a point and get its absolute position. Or we can use some other data source such as odometry. And by odometry, I mean it's the sensors that can estimate self-motion, usually from things like wheel encoders or heading sensors. So this is fairly accurate over short distances, but can drift over longer distances. But it is a source of unambiguous scale. So this is how I set up this particular algorithm. This part minimizes the projection error between the observed image point and the predicted image point based on the current guess of the pose and the current guess of the 3D point. But this term minimizes the difference between the observed odometry data and the predicted odometry data based on the poses that we think we have. So this constrains the scale of the solution then. And the notation here with the subscript means that if we have a covariance matrix for the measurement, we can weight the measurements based on that covariance matrix according to this function here. So we'll minimize this function E using the nonlinear least squares algorithms such as Levenberg-Marquardt. So bundle adjust is computationally expensive. One way to reduce the number of variables to compute is to use a sliding window like this. So rather than computing the poses for all the frames, just compute it for the last n frames, or 7, in this case 7 poses. And we'll also need a good initial guess. The pose guesses can come from odometry. The point guesses can come from triangulation. This is the pseudocode for the overall algorithm flow. Basically just runs through this while we have new data. It only computes the poses, runs the bundle adjust if we're at a keyframe, which occurs every 1.5 to 3 meters. There's some results from a run here. Let me start these up. So you see these red points in the background. Red means we're tracking these points in 2D, but we don't have 3D information. Orange indicates that we have computed the location via triangulation, and yellow means that there's a bundle adjust solution. So these actually all run simultaneously. So if you can see points in the clouds or points on the back of the truck are maintained in red because we were never able to triangulate those successfully because they don't move. And these show an animation of the computed results. So it shows the 3D points that were computed as well as their uncertainties as drawn as an ellipsoid. And this is a top view here. Yellow indicates that the point is currently being tracked, and blue indicates that it is no longer tracked but is archived. And just to summarize some of the runs over quite long distances, this one was done over 1.1 kilometers, has 3,800 points that were archived. This is done in more of an open field. This is the video I showed earlier, 4.2 kilometers, 5,700 points. And this one, 4.5 kilometers, 2,000 or 24,000 landmarks.